Questions about anything? Last time or anything? Let's see, I wrote out a thing there that I mentioned last time, but maybe didn't emphasize quite enough. When you're dealing with terms in a series that are greater than or equal to 0, so non-negative, then of course that's the partial sums would be increasing, an increasing sequence with less than or equals to's in the meaning of increasing. Because every time every next one you're adding a term, and those terms are greater than or equal to 0, so it can only get bigger. And we know facts about increasing sequences. If they're bounded above, then we know they converge to the soup. And so if that series sum is bounded, then it converges, and the limit is the soup. And if that doesn't happen, then the limit goes off to plus infinity. So there's two possibilities. It's either plus infinity or the limit exists. That's an important fact to know. And I wanted to sort of slow down and dwell on this material because there's lots of interesting examples to think about, kind of fun things to think about too. I think I'll start out today with an example. It's kind of fun. We've seen it before when we were studying sequences, but there's a classic trick in analyzing series of realizing the sum as a telescoping series. So let's see, this would be 1 over 1 times 2 plus 1 over 2 times 3 plus etc. The general term is 1 over n times n plus 1. And if you think about that, it's natural to think of partial fractions. So usually you like x's instead of n's, but this kind of reasoning works fine with n's in places of x. Partial fractions tells you this would be a over n plus b over n plus 1. And you remember what to do with partial fractions. You multiply that by the denominator of the left-hand side, so n times n plus 1. And when you do that, you get a big fat 1 on the left. Here you get a times n plus 1 plus b times n, which you can pull apart and write as a plus b times n plus constant term a. That's supposed to be equal and true for all n. And so you realize, oh, I see, there's only one way that can be true. This should have a 0 times n plus 1. The a plus b has to be equal to 0. And the a term has to be equal to 1. So you get two equations, and they are a plus b equals 0 and a equals 1. So that determines a, and so now we get b equals minus a equals minus 1. You can probably do this by inspection, but you now have that 1 over n plus 1 is a is 1, so that'd be 1 over n minus 1 over n plus 1. So that tells that sum, our sum, let's call it Sn, would be that sum. It'd be 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus dot 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 out to, maybe I should do one more here so you see the telescoping business. 1 over 3 minus 1 over 4 plus dot 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 1 over n minus 1 over n plus 1. And then you realize, aha, these two cancel, the next two would cancel, and that would happen all the way out to this last term. But then there's nothing to cancel that very last one. And there's nothing to cancel the very first one. So the nth partial sum is 1 minus 1 over n plus 1. And of course that tends to 1 minus 0 as n goes to infinity. And so our sum, we determine 1 over n times n plus 1 is equal to 1. It's kind of interesting. And that looks like 1 over n squared. And so knowing this, we can determine that 1 over n squared converges. Because that would be a sum of positive terms, so it's increasing. And you can bound it now that you have this fact. I'll let you read about that kind of thing in the book. So 1 over n plus n times n plus 1 looks a lot like 1 over n squared. Let's see, how would I do it? Let's think about this. So here's a problem. 1 over n times n plus 1 kind of looks like 1 over n squared in size. It's just off by a little bit. And so what could I do here? Let's think about it. If I wanted to use known facts, what could I do? Well, n plus 1 is bigger than n. So 1 over n plus 1 times n plus 1 would be strictly less than 1 over n times n plus 1. Okay, and those are just like 1 over n squared. There's just n plus 1 there. And so, in fact, you can, by comparing the tail end of those series, you can see that you can bound that thing above. Let's see, how would I bound it? So I'd have 1 plus 1/2 plus 1 over n. Let's make it 1 over n plus 1. I'll leave this 1 here. That's a 1. But then the 1 over this stuff is the sum of the 1 over n plus 1s, and that would be less than, this would be less than 1 over 2 times, 1 times 2. What am I doing? I'm doing squares here. Squares. That would be less than 1 over 1 times 2, etc. This last one would be plus dot 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 plus 1 over n times n plus 1. And this series converges to 1, so this whole thing is less than 2. And so that fact above would imply that we get converges. Bounded above, and they're positive terms in the series, so it converges to something less than 2, less than or equal to 2. Well, that's the kind of trick we can do until we get enough facts that we can use theorems in place of tricks. This is a fun thing to think about that I guess I must have seen it before. But another example is the famous harmonic series. The sum as n goes from 1 to infinity, 1 over n, diverges. You probably saw that in freshman calculus via the integral test. I'll say that more about that in a minute because it's a beautiful thing and maybe is the preferred way of thinking about it. But the famous harmonic series is famous because it diverges even though the terms go to 0. So if you want an example of a series that diverges, even in spite of the terms going to 0, this is the one. Even though the terms go to 0. So the sum of 1 over n squared, those terms go to 0 faster, and that actually converges. These don't go to 0 fast enough, and it diverges. But here's a kind of a cool thing to think about. Here's the y for today. The first y. I'll give you a second y later. Let's suppose this thing converges. So we'd have a sum equals the sum of 1 over n from 1 to infinity. Okay, here's a sneaky trick. Then 1 over 1 plus, okay, I'll write s, would be equal to this sum, 1 over 2. I'm going to write it like this, 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus, in general, 1 over n plus 1 over n plus 1. Plus. Okay. The second one of those things is 2, 4, 6, 8. And those are, this is strictly less than. Sorry, it's strictly greater than 1/2 plus a half. Because the numbers are getting bigger. And this is strictly greater than 1/4 plus a fourth. And 1/6 plus a sixth. Of course, this would be, who cares? Yeah, and so look at this is, this thing is 1 plus a half plus a third. In other words, it's a harmonic sequence all over again. And that's a strict greater than because that first term is strictly greater. So of course, whatever this sum is, converges to, it is strictly greater than the number s. And so this whole thing is equal to s. So if that series converges, then this simple rearrangement of the series would show that s is greater than s. So we deduce that the sum is greater than the sum. So of course that our assumption that that series converges must be false. That's a fun observation. Let's see, why is that called that's called the harmonic. I should write that up there. Okay, I guess I'll write it down here. This sum is called the harmonic series. And I'll explain why I kind of like this subject. 1 over n is the harmonic series. kind of for musical reasons going back to Pythagoras. So here's a vibrating string. So a vibrating string would be stretched from 0 to some length and then be allowed to vibrate. So if you ever plucked a guitar, you'd see the vibration looking like this under a strobe light. That would be the pitch of the string. Well, then Pythagoras realized if you touch that string lightly right in the middle, so you touch it, and then if you look at it under a strobe light, you'll see that the vibrations now look like this, and the pitch would go up an octave. Okay, so this is the pitch of the string that you would hear when you pluck it. This is 1 octave higher. And then if you were to touch it at the 1/3 mark, so this is the L/2 mark. If you touch it at the L/3 mark, then it would vibrate like that. If you looked at it under a strobe light, it would look like that. And that would be touching it lightly at the L/3 mark. That's an octave and a fifth higher. Okay, so it's like L/2, L/3. The next one would be L/4. That would be 2 octaves higher. So this is an octave and a fifth. Perfect fifth. Anyway, the notes, I'll tell you what happens when you do this business. More space. Okay, the first note's going to be C. C. That's the n=1. That's the fundamental pitch of the string. Then, when you touch it in the middle, it goes up an octave. That's the octave above, C, another C. An octave and a fifth would be the G. Let's see, I should be make clefs here. That's the bass clef. Oops, yeah. C. The next one would be a G. Then the next one is 2 octaves higher. That's a C again. So this is n=3. When you do it in a third, this is when you do it in a fourth. Then the next one would be E. The next one would be G. And then they start getting funky. Let's see, E, G. The next one would be a B flat. And then the next one would be a C. And they start getting incredibly close together. So that's kind of like a harmonic series, because the terms 1 over n are getting closer and closer. They're getting really close together and adding little tiny small amounts. And so this is a very slow growing thing. But the next one would be a D. Let's see, what that number B flat is the 7th one. This is 5, 6, 7, 8, 9. And that's why it's called a harmonic sequence. Put those over here. And those are really interesting to study. The frequencies go up exponentially. So the frequency doubles when you go up an octave. And going up 2 octaves, it doubles twice, so it's 4 times bigger. And so even though this is a very slow growing thing, the frequencies are growing fast, exponentially. And so this whole subject of music is fascinating. And in fact, I teach this material when I teach Fourier series. It's a very fun thing to, you realize, oh, Fourier series have a lot to do with this, because Fourier series were invented to solve the vibrating string problem. And the book shows you, even though that it's a very slow-growing series, so this is a good thing to read in the book, a fact. If I take the partial sums, Sn, that would be the sum from 1 to n of Sn, of the 1 over n's, is a very slow-growing sequence. It grows so slow that you might think, oh my gosh, this has to converge, because it's just going nowhere. And it's kind of like those notes there. They're getting close. This is exactly the notes you would get on a bugle. When you do, the only notes a bugle can play are those notes. And you can play arbitrarily high notes on a bugle if you've got the lip for it. It's a very slow growing sequence, but it grows indefinitely. So from the point of view of music, that means on a bugle, you can play arbitrarily high notes, and they get closer and closer together. And eventually, of course, they get less than a half a step apart. Questions about that? It's a fun subject, yeah.
The last time we learned that something, in order to go to infinity, that means that for any large n, you could find like a sum that's greater than that.
Right, but you might have to wait forever in this case. It'd be a gigantic, I mean, the book describes how long you'd have to wait. If you did added one a second, you'd have to wait an eon to get to something reasonably big. Okay, so I'm going to get to the nitty-gritty today. We'll have a couple of very important comparison tests. And the most basic one is one we've already seen. It's kind of like the squeeze theorem. Let's suppose I have two sequences. And I have 0 is less than or equal to xn is less than or equal to yn. Then an easy thing to determine, it's like this, by the squeeze theorem, in fact. I guess it's not the squeeze theorem. But it's an easy thing to check. Let's see, if the yn series converges, then the xn would have to, because it's obviously less. So I don't think I'll write out the proof of these things. So if the right-hand side converges, that would imply the sum of the xn's also converges. So if I was going to give you a proof of that, I would say, oh yeah, theyn's, the partial sums is an increasing thing. If it converges, it's bounded above. And that would mean the xn series sum would also be bounded above. So it would have to converge. And then you convince yourself that the sup of the smaller one would have to be less than or equal to the sup of the bigger one. So the big one converges implies the smaller one does. And of course, the limits those converge. And of course, the limits are what they should be. The smaller one limit would be smaller than the right-hand side. Okay, so that's the first version. And the other version is that if the small one diverges, then the big one has to diverge, because it would go to infinity and not be bounded. So if the left-hand side diverges, See, this is the convergence one. That's the one that would imply the right-hand side diverges. And of course, in that case, they're both equal to plus infinity. So that's pretty elementary, just thinking about increasing sequences and soups. That's the first comparison test today. I'm going to get another fancier one in a minute, but first I want to take a time out and think about a famous subject of P-series. One over the sum of the harmonic series is an example of a P-series with P equal 1. So the sum of 1 to infinity of 1 over n to the P. It's a famous category of series, and the famous fact is that it converges when P is bigger than 1. And it diverges when, let's see, if P was 0, that'd be 1 plus 1 plus 1. So that certainly diverges. So 0 less than or equal to P. 1 is the critical thing. 1 is the harmonic series. So that's where it starts suddenly converging after that. So, for example, so sum of 1 over square root of n diverges. But the sum of 1 to infinity of 1 to the n to the 1.00001 converges. Stuff like that. Well, the interesting thing you learned from the book this week is that you can deduce those facts by playing around with inequalities and being clever. I showed you a couple of the clever things that I could have done to see that the harmonic series diverges. Those clever things are neat and interesting, but I much prefer to explain this in terms of the freshman calculus integral test. So from freshman calculus, this is the primary example in studying the integral test. It's worth sort of pulling out of the dust. Let me draw a picture. The integral test is really easy to explain, and it's a fun thing to graph. I'm going to graph 1 over x to the p. It blows up. It's 1 at 1, and then it shrinks. It's not very good. Blows up. It's 1 at 1, and then it shrinks. Okay, so here's 1. 1 at 1. 2, 3, 4, 5, dot, 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 n plus 1. Okay, this is a graph of 1 over x to the p. Looks like that. Notice that it's a decreasing function. Okay, so that's the key to this thing. And so if I take, this is the one term right here. So the area of this rectangle would be 1 over 1 to the p times the base is 1. The area of the next rectangle would be 1 over 2 to the p times 1. So it's like that. And the next one would be 1 over 3 to the p times 1. That would be the area of that rectangle, etc. And notice that those things contain the area under the curve. Let's say, so 1 over n, this last one, would go out here and contain this one. And so that sum would be bigger than the area under the curve from 1 to n plus 1. Okay, what color? Orange, how about? Well, I don't want to start with, I don't want to go underneath that left-hand, I don't want to go underneath that place where the curve blows up. So when I go underneath the curve, I'm going to start with 2. 1 over 2 to the p times 1 would be the area of that underneath the orange line there. That's underneath the curve, and so that area would be less than the area under the curve. And 1 over 3 to the p would be this orange line, times 1 is the area under that orange line. That's less than the area under curve there, et cetera, et cetera. And so these, it's harder to see when you get out here. And let's see. I'm going to, yeah, so this last one, God, it's impossible to see, isn't it? Here. Okay, so when you look at that picture and realize because that function is decreasing, the max is at the left-hand side and the min is at the right-hand side there. And so it's just a matter of understanding areas that, let's see, which of the small ones would start at 1 over 2 to the p plus 1 over 3 to the p. The last one would be 1 over n plus 1 to the p. Those are the little orange rectangles. They would be underneath that would be underneath the curve, so that would be less than the area from 1 to n plus 1 of 1 over x to the p dx. And now for the purple ones, that's less than, the purple ones are above the curve, so that's less than 1 over 1 to the p plus, the last one is 1 over n to the p. Okay, so we have two facts to deal with here. If these sums are bounded above, then that sum converges. So, if this integral is finite, if this integral is finite, if it's bounded, so finite should mean these things are bounded as n goes to infinity. Yeah, so that's what I want to say. This is bounded, meaning the area is finite as n goes to infinity. That would imply the left-hand side is bounded. So convergent by the facts of the day. Okay. And on the right-hand side, if this is unbounded, as n goes to infinity, capital N goes to infinity, that would imply that the right-hand side also goes off to infinity. And of course, those are the tail ends of the series. Those things, divergence or convergence are equivalent to the divergence or convergence of our series. So that's a quick review of the integral test. Now we know a lot more than we did back then. This very much depends on the least upper bound principle to understand properly. Yeah?
If the term in the middle is unbounded, can we see the left side is unbounded too?
Well, the left side is very similar to the right side. If I added 1 to the left side and added 1 over n plus 1 to the p to the right side, they'd be equal. And so understanding one of those means you understand both of them.
Yeah, but I mean, if the middle term is unbounded, so the left side is also unbounded.
It would also be unbounded. We could deduce that because they're so relatable. But the inequality only gives me one direction. Right? You could figure it out by being fancier. Yeah. Okay, so those integrals are simple. If p is not equal to 1, then those integrals are simple to calculate because an antiderivative for x to the minus p dx would be equal to 1 over minus p plus 1 x to the minus p plus 1. And then you realize, oh, p equal 1 is a very critical thing, because then I would get a negative power here. I either get a negative power or I get a positive power. The negative powers converge, and the positive powers diverge. So minus p plus 1 less than 0 is bad. No, it's good. Minus p plus 1 greater than 0 is bad. Minus p plus 1 less than 0 is good from the point of view of convergence. And of course, the p equal 1 case is totally different. That's when you get the natural log function equals log n plus 1 minus log of 1, which is 0. And of course, that goes to infinity. It's a thing you learn in freshman calculus. You figure that out from first principles, that the log tends to infinity as x goes to infinity. Questions about any of that? That's just a remark because it's kind of, we haven't studied logs or exponentials or any of that stuff yet, and we will later. But this is the way any math person would think about this p-series business. Another fun fact today is that the harmonic series is bad, but the alternating harmonic series converges. So that'd be 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus etc. converges. And you would have seen this in freshman calculus too. It's called the alternating series test. Okay, so we would have terms xn strictly positive, and the xn's are decreasing. And important, the xn's tend to 0, just like 1 over n does. They're all positive. They're getting smaller and smaller, and they definitely tend to 0. Then, the alternating series you get from these let's see, I want the first one to be positive, so that would be minus 1, not to the n, but to the n plus 1. Then the first term would start out being positive. And after that, they would alternate. Converges. And I'll sketch the demonstration rather than do it. So let's see. L would be x1 minus x2 plus x3 minus x4 plus etc. Okay, so why is this thing true? I like to draw a picture here. I need a limit for myself here. I'll make it orange. That's the limit L. X1 starts out 1, 2, 3, 4, 5. X1 starts out someplace. Then I'm going to subtract x2. So x1, I'm going to do it here. X2 is smaller than x1. So this distance here is my x2 distance. It's red. Here's x1. Make this red. This is x1 minus x2. And then the next one, I'm going to add an x3. And that's less than x2. So here I would add x3, and it's less than x2. So convince yourself that that is below the top red dot. And now I'm going to subtract x4, and it's less than x3. Okay. There's no red dots on this stuff. Anyway, the odd red dots are a decreasing sequence, and the even red dots are an increasing sequence. Okay, so if I was going to prove this to death, which I am kind of doing, let's see, I'll do one more of those things. The next one would be take this one and add something less than x4. That's the x5 distance. That gets me here. Okay. So when you start looking at that picture and believing it, you see that the odd, what did I do? My x1 is at 1. Okay, yeah, that's right. My odd terms, that would be x to the 2n, x sub 2n minus 1, are decreasing. You can just see it. I believe it. They're decreasing, and they're bounded below by any one of those red dots on the bottom there. The easiest one to bound below is the first one. And bounded below by x1 minus x2, that first red dot. So the odd terms, let's see, these are the odd term. I'm actually graphing the partial sums. I'm not graphing the xn's. So this is actually the partial sum. S sub n is x1 minus x2 plus or minus 1 times xn, whatever it is. That's the SNs. Those are the red dots. That I drew here. Okay, the odd ones are decreasing and bounded below, so the odd ones converge. The even ones are increasing and bounded above. So they both converge. And of course, they're going to converge to the limit. They're bounded above. Those are bounded above by x1. That's the easiest thing to see. So they both converge. And let's see. So Sn 2n minus 1 converges to a limit. Let's call it limit sub odd. And S sub 2n converges to a limit. Let's call it limit sub even. And those two are the same. Because what's the easy thing to do? S2n minus S2n minus 1. Well, let me do I'll do S2. Let me do S2n plus 1 minus S2n. That's X2n plus 1. The odd ones are positive. I didn't want it to be negative. Okay, and if I take limits, this one would tend to the L sub odd. This one would tend to L sub even. And these we know, or given, tend to 0. So that's how I can say that these are the same. And of course, those being the same, they're the limit of the series. Summation minus 1 to the n plus 1 xn equals that limit. That's kind of a fun thing. The last big theorem I want to mention today is called the limit comparison test. And it's considerably more powerful than just the basic comparison test. Okay, so the limit comparison test is about series with positive terms. So we'll have xn and yn strictly positive. So we need them strictly positive, and all the yns strictly positive. And it tells us that we can compare the tail ends of those series if we know that the ratio tends to a limit. Let's suppose R equals the limit of xn over yn exists. Of course, it's greater or equal to 0 because those terms are positive. So the case, if R is something positive, then the two series have the same behavior. Then the summation of